Hello students, in the last session we completed arrangement of elements in the periodic table, and then we did see the IUPAC nomenclature for the elements which has atomic number greater than 100. So that step was done. Then we saw the atomic radius, isn't it? So based on the periodic trends, the first thing that we saw was atomic radius. So to find the atomic radius, depending on the nature of the metal or non-metal, we had different radius that we were supposed to find, which was like metallic radius, covalent radius, and then the van der Waals radius. So you should be clear with those stuff. Finally, we saw the ionic radius. Got it? So the negative ions will have greater radius when compared to that of the cation. That's what we saw over there. And finally, we did see the ionization enthalpy. So ionization enthalpy means the amount of energy that is needed to break one electron from a neutral atom will be the ionization enthalpy. If it was the first electron that I'm going to break, then it will be first ionization enthalpy. If it's going to be the next one, then you would have got second, third ionization enthalpy, and so on, right? So you should be clear with the exceptions that we have seen. What it has to be clear. Then in this session, we will see the next two terms, which will be the electron gain enthalpy. Got it? So in ionization enthalpy, we actually removed. With the case of electron gain enthalpy, the name clearly suggests we are going to add one electron to it, right? We will see it indeed. We will see it in detail. Then we have to see electronegativity. Got it? So those are the two chemistry terms that we need to study in this session. Then finally, you will see based on the periodic trends, we just need to know the acidic and then the basic strength of different elements, which will be the oxides, hydrides, and then the oxyacids, right? So we'll see all those stuff, right? So those are something that we are going to see in the session, fine? Now we'll see electron gain enthalpy. See, the name itself clearly tells you. Here I'm just going to put one extra electron to the neutral atom, right? So it's going to gain one electron in the situation, fine. So when I'm going to put one electron into the atom, two things is also possible. Either it could release the energy. Got it? When it releases energy, that's negative. That too is possible. That would be the majority of the situation. Or I could be the one who is going to push that electron into that atom, right? Okay, so that one is also possible. When I push that electron, obviously I'll be the one who is going to give that energy to it. In that situation, it's going to be positive, right? So both those situations is also possible. In majority of the situation, it will obviously release the energy, right? So even with the case of electron gain enthalpy, in majority of the situation, you'll get exothermic, which means you'll have that negative sign, right? But with the case of ionization enthalpy, it will always be positive, which means I'll be the one who will break that electron from the neutral species, neutral atom, right? Because neutral atom in itself is stable. When I'm supposed to remove that electron from that neutral atom, obviously I should be the one who needs to give that energy, right? So with the case of ionization enthalpy, that's going to be positive. With the case of electron gain enthalpy, it will mainly be negative. At times it can also be positive, right? So we will see those conditions where it's going to be positive. So you should be clear with this term, which is like electron gain enthalpy. So enthalpy simply means the energy that's involving in that situation, right? So we will learn more about enthalpy, internal energy, and all those stuff in upcoming chapters that will be in the thermodynamics. As if now what you need to know is, while you're having a chemical reaction, what was the energy change? Okay, how much amount of energy got released? That's what is meant by enthalpy, right? It has to be clear. So here the enthalpy change when electron is added to a neutral gas atom is what is meant by electron gain enthalpy, right? So when you have an atomic gas and then you're gonna pump an electron into it, and then it becomes obviously negative ion or anion in the situation in the gaseous state, right? So what will happen in the situation is either it could be exothermic or endothermic, which means either it can release energy or we'll be the one who will give the energy to it, right? Both those conditions are possible, fine. But when in majority of the situation, it will be the one that's going to release the energy. So now we'll see what will be the trend across the period and down the road. This too will be same like that of the ionization enthalpy. Got it? You shouldn't consider the negative sign, right? So we'll just be worried about the magnitude, amount of energy that's going to get released. That's what we will concentrate on. Fine. So across the period, if you just look across the period, how will it be? You will have like effective nuclear charge to increase across the period, right? So initially the atom will be larger, then as you move across the period it will shrink, right? So same thing is going to happen over here. So as it starts shrinking, you obviously know the effective nuclear charge is greater. Same way, the electron that I'm going to put is going to come very close to the nucleus. Okay, as it comes very close to the nucleus, it simply means it has released a lot of energy to the surrounding, right? Therefore, across the period, because the atomic radius is also less, same way effective nuclear charge is also more, therefore the pull is going to be greater for a greater distance, which simply means there will be large amount of energy released, right? So across the period, electron gain enthalpy is going to increase. You have to be clear. In this situation, same as that of the previous case, it's going to be negative. Still, you shouldn't consider the negative sign, only the magnitude has to be considered, right? So electron gain enthalpy is going to increases, right? Then with the case of down the group, what will happen as you move down the group? Yeah, it has to be obvious. We are just going to fill in the next subshell, next principal quantum number or shell. Therefore, in this situation, as you move down the group, you are going to have the greater atomic radius. Okay, therefore effective nuclear charge will also be less because of the inner shielding of that completely filled shells. Okay, so those inner filled electrons is gonna shield the maximum nuclear charge, therefore effective nuclear charge is gonna be less, the radius is also greater, and the electron that's gonna come into that atom is gonna be farther away from that of the nucleus when compared to that of the element that is above, right? Therefore, as you move down the group, the electron gain enthalpy is gonna decrease. That's gonna be the opposite to that of the across the period. It has to be clear. Therefore, here in this situation, electron gain enthalpy decreases. Got it? It has to be clear. No doubt should be there. Then let us see some exceptions to it. How to consider those stuff. Yeah. Here to work on the exception, I'll just mainly consider the p block elements. Okay, so as far as s block elements is concerned, that will work out properly. So with the case of p block elements, you'll have some exceptions to it. We'll see all those exceptions that we are supposed to see over here. So first let us start with the oxygen family, then we will see the halogens, okay, and then nitrogen family, and then finally the noble gases. Got it? So with the case of oxygen family, what will you have? You would have got like oxygen. I'll just tell you down the group. Okay, oxygen, sulfur, selenium, tellurium, and then the polonium, right? So that's how it's gonna be. So if you look in this pattern, it should be that as you move down the group, it has to decrease, isn't it? Yeah. Yes, the electron gain enthalpy has to decrease because you're going to put electron farther away from the nucleus. Same way, effective nuclear charge is also going to be less. Got it? So what we expect over here is oxygen should be at the beginning, and it should have the maximum energy released, right? But that's not going to be the case over here. First, you're going to have the sulfur. Okay, so first you'll end up having the sulfur. Okay, then comes selenium. First, that's sulfur. Then comes selenium. Then you would have had tellurium, polonium. Finally you'll get the oxygen. Okay, so oxygen will be at the last. Okay, so this is something odd. I'll tell you the reason why it is in this pattern. That's because when you look at the oxygen, the oxygen just has 8 electrons altogether, and then you would have got like 6 electrons on the outer shell, right? So 2 will be for the oneness, and then you would have got 6 electrons on the outer shell, which is the valence shell. So in that situation, that shell is going to be very close to the nucleus. Got it? When you consider that surface area, that is like very close to the nucleus, therefore the surface area is less. In that situation, those 6 electrons are the electron density for those 6 electrons is going to be more. Okay, so those 6 electron will just occupy that small surface area in a really closed manner. Okay, therefore electron density over there will be greater, right? You should get the intuition. Got it? So here that second shell is going to be very close to the nucleus, and by the way, you have got like 6 electrons. Because of those 6 electrons, that's going to be densely populated. When you're going to put that one electron from the when you're going to push that one electron from the outside, so the amount of energy released will be less when compared to that of the sulfur. Okay, same way if you look at the sulfur, that's going to be 3, that's going to be the third principal quantum number, okay, or the third shell. So with the case of third shell, that surface area is going to be greater. Same way you would have got like 6 electrons over there, isn't it, in the outer shell? When you have got like 6 electrons over there, that's going to be spaciously arranged, therefore you wouldn't have more electron repulsion between the electron that's going to come from the outside and the electron that is in that shell, right? So there it would be able to just accommodate into that shell very properly. Okay, therefore more amount of energy will be released, right? So with the case of the oxygen, there were more electron repulsion between the outer electron that I'm going to push it into it. Same way the valence electrons, got it? Because they are densely packed. But with the case of sulfur, that's a little bit farther away from the nucleus. Therefore, you would have got like more surface area for those 6 outer electrons. Therefore, in that situation, the electron that I'm going to push it from the outside is going to release more energy because there wasn't much repulsion from the electron, right? You should get this thinking and logic. So, same argument could be made for selenium, tellurium, polonium, right? As you move away, what would have happened is the effective nuclear charge is going to decrease, okay? Therefore, it's not able to pull it much greater into it, right? So that's the intuition. So here I've moved down the group as we expected. As we move down the group, the electron gain enthalpy is going to be less, okay? As we move down the group, the electron gain enthalpy is going to be less, but only exception over there is the oxygen, which comes at the very last, because with the case of oxygen, it was very close. That particular shell was very close to the nucleus. Therefore, you had more electron density, concentrated electron in that particular shell, right? So that's the intuition that you need to know. You have to be clear, right? Whatever the case it is, you have to memorize this pattern as such, right? So they will ask question based on this pattern. So you have to be clear with this pattern that I've given over here. Then what you had is next one will be for the halogens, okay? So even for the halogen, I'm gonna make the same argument. For the halogen, you would have got fluorine, chlorine, bromine, iodine, yttrium, right? But here I'm just gonna flip first two. So you would have got like chlorine, fluorine, bromine, iodine, yttrium, okay? So first you would have got chlorine, then comes the fluorine, okay? So chlorine, fluorine, bromine, iodine, and then finally you would have got the yttrium, right? Same argument, but with the case of oxygen it came very last, okay? But with the case of fluorine it comes next to the chlorine itself, right? So same argument, same logic, you do the experiment and you find the result. Got it? With the case of oxygen, in that situation, when compared to all these stuff, this was at the last, okay? But with the case of chlorine, okay, chlorine, fluorine in this halogen series, what has happened is fluorine came next to that of the chlorine, right? You have to memorize this one with the same pattern itself. You're left with no other choice, right? It has to be clear, right? Same way, here I have just given the statement which I've already told you, which means negative sign is not considered while arranging the descending order. It just signifies that energy is released when electron is added to the atom. So you shouldn't consider the negative sign, okay? Yeah, it just represent here. I've just matched with the magnitude. Okay, so with respect to magnitude, chlorine will have the maximum amount of energy released. Fluorine will be the next, and then comes the bromine, iodine, and finally you would have got the yttrium. Okay, so this one has to be clear. So now we are done with the two family, which is oxygen family and then the halogen family. Next, just two more is left, which will be the nitrogen family. So it will be odd, right? And then same way the noble gases. Okay, so these two will have some different arrangement into it. So with the case of nitrogen family, something that you have already seen with respect to ionization enthalpy, right? So that has half filled shell, right? So when you have got like half filled shell, that's going to be more stable, okay? Same way here also, nitrogen has half filled p shell, which is responsible for its anomalous behavior, okay? And then you have got nitrogen has positive electron gain enthalpy. So here the reason for the positive electron gain enthalpy is because of this half filled p shell, okay? So it is like positive, which means I am the one who is going to give that energy to the electron to push it into the atom, right? So initially the nitrogen had symmetrical structure over there with the case of arrangement. Therefore, when I need to push one more electron into it, I'll be the one who is responsible to give that extra energy to push it into it. Okay. Therefore, here in this situation, you have got like positive electron gain enthalpy. So nitrogen has positive electron gain enthalpy. Okay. With the case of about two series, you have got negative, but the arrangement was something odd. But in this situation, nitrogen had positive electron gain enthalpy itself, right? So then after nitrogen, you would have got like phosphorus, arsenic, antimony, bismuth, isn't it? So let me write all those stuff. You would have got it in the same pattern itself. So you would have got like nitrogen wouldn't come into picture. Then rest all other five elements, rest all other four elements will have negative values into it. So you would have got like phosphorus, arsenic, yeah, right. Then you would have got antimony and then the bismuth, okay? Okay, so you would have got like phosphorus, arsenic, antimony, and then the bismuth. Got it? So with respect to these elements, you will still have negative electron gain enthalpy. Okay, so it's gonna be negative, but the point is it would have released energy, but we know as we move down the group, electron gain enthalpy has to decrease. But in this situation, as you move down the group, the electron gain enthalpy is going to increase. Okay, which means with the case of phosphorus, the energy released was less when compared to that of the arsenic. Arsenic released more energy. The same argument, the phosphorus, you still had half-filled p subshell and then it was close to the nucleus. Okay, so in that situation, the energy released was less. As you move farther away, those three electrons will be spaciously arranged. Therefore, putting one extra electron wouldn't disturb that symmetrical structure, which means they have like enough space into it. Therefore, you wouldn't have any electron repulsion in that situation. Okay, so that's the intuition that you need to develop. Okay, so phosphorus, arsenic, antimony, and then the bismuth. Okay, so in the series also, it was actually increasing down the group. It wasn't actually decreasing down the group, it was increasing down the group. With the case of phosphorus, still bismuth energy was released, but the nitrogen was extreme opposite. In that situation, I was the one who gave the energy to push that electron into the neutral atom, right? So this is something that you need to know this with respect to nitrogen family. Then finally you have got the noble gases. Okay, so noble gases, in this situation, this is like a perfectly stable case, right? So when it is in the perfectly stable state, if I have to push extra electron to it, I have to overcome that stability, right? Therefore, I'll be the one who is going to give the energy, which means the electron gain enthalpy is going to be positive with the case of noble gases, right? So electron gain enthalpy of noble gases are positive because it has attained stable configuration and there is no place for incoming electrons, which means I'm the one who is going to put that extra electron to the next valence shell. So I just need to push that electron into that atom, right? So here if you just look, same way, as you move down the group, the amount of energy that is needed to push it will decrease, and helium will only be the exception in this case. Okay, so even in this situation, as you move down the group, okay, the magnitude of electron gain enthalpy is gonna decrease, which means initially you would have got like neon. Okay, it starts with the neon. First you would have got neon, then you would have got like argon, then you would have got like krypton. So neon, argon, krypton, xenon, radon. Finally, you would have got like helium, right? And the only exception over here is going to be like helium. Got it? See, if you look at this series, initially, as you move down the group, obviously the way we expected was like electron gain enthalpy should decrease. Even though it is positive over here, still the electron gain enthalpy is going to decrease. For the neon, I just need to give more energy to pump one more extra electron. Okay. So with the case of argon, that's going to be less when compared to this neon. Okay. But the only exception over here is the helium that comes at the very last of the series. Even though for helium, still I just need to give energy. But when compared to all these noble gases, helium requires less amount of energy to pump that one electron into it, right? So here also you could make the same argument over here, right? So there were like only two electrons in the first shell, which wasn't good enough in pushing us away in pushing us away that one electron that I'm going to extra pump into it, right? But with the case of rest all other gases over here, noble gases over here, pushing in one electron was tougher because you had like eight filled filled outer valence electrons. Okay, so therefore in that situation it was hard for me to push one more electron to it, but with the case of helium only just two electrons were there, therefore it was easy when compared to rest other noble gases, right? So however it is, you do the experiment, you get the result, and then just get the argument based on the result that you're gonna see, right? So that's what we have done over here. So this is what you need to know regarding the series with respect to P block elements with the case of electron gain enthalpy, right? You just need to memorize it as such, right? The reason why I gave you those arguments is because you might get like statement based sum where they'll ask you the reason. If they ask you to get the reason, you should know why does this oxygen come at the very last. Okay, the reason is because of its size. Okay, something of that sort. You have to get that intuition and thinking, right? Got it? You should be clear. So I'm just done with the oxygen family, chlorine family, and then the nitrogen family. So with the case of nitrogen family, it was exactly opposite, right? It started with the phosphorus has the lowest electron gain enthalpy, and then the bismuth had the maximum electron gain enthalpy because of the stable, yeah, half-filled stable p shell. Okay. Then with the case of noble gases, it was what we expected, but the point is it was positive itself, right? So neon got the maximum electron gain enthalpy with respect to positive, which means I have to give energy to it, and the helium got the very least electron gain enthalpy. Yeah, right. So this is what you need to know regarding the p block elements. And you have got like beryllium, and then the magnesium has positive electron gain enthalpy as it has half filled 2s and then the 3s subshell, right? So beryllium and magnesium are going to be the s block elements. With the case of beryllium and then the magnesium, it was like 2s 3s fully filled subshell. Yeah, 2s fully filled subshell. Therefore I'll be the one who is going to give the energy to pump the next electron, which will be filled in the 2p and then the 3p subshell, right? It has to be obvious and clear. You shouldn't have any doubt in the statements that I've written over here. You have to be clear with the arguments that I've made also. So finally, you have got the electron affinity. Okay, so with the case of electron affinity, it's gonna be negative of electron gain enthalpy. Okay, so whatever value that's gonna be negative with the case of electron gain enthalpy, I know in majority of the situation the energy would have been released while it accepts one electron, right? So therefore it's going to be negative. If I have to get the positive value of that negative value, just plug in one more negative sign before it, so that gives you the negative of negative value. With the case of electron affinity, that's going to be positive for the elements which has negative electron gain enthalpy. Same way with the case of nitrogen that has positive electron gain enthalpy, that's going to get you the negative electron affinity. Okay, so those two stuff will be oppositely related, right? So that's what you need to know regarding electron affinity. Just a negative sign before the electron gain enthalpy will give you electron affinity. Now we are in the last part of this periodic trends, that's going to be electronegativity. Next one is electronegativity. First, let me read the statement, then I'll explain you. The statement is the relative tendency of an atom to attract the shared electron pair towards itself. Okay, so it's the ability of an atom to attract that electron pair, fine, which has to be shared. Okay, so to explain you this one, let me take the classic example, which will be the hydrofluoric acid. I'm going to get this molecule. Okay, so it has to be in its bonded state. When it is in the bonded state, okay, there can be a number of bonds, okay, depending on the situation. But here I'm just going to take a molecule which has just single bond between those two atom, right? We will learn more about covalent ionic bond in the next chapter. As if now from the lower grades you should know that is going to be single bond between the hydrogen and then the fluorine. Okay, this has to be known. Okay, so if that's going to be the case, you would have got like two electrons over here, right? So when you have got like two electrons over here, it is shared. Okay, it's not going to be shared in this fashion. So 50% will be for this hydrogen and the same 50% will be for this fluorine. Okay, that's not how it's going to be shared, because one has more tendency to attract the electron. Got it? In this situation, the fluorine had like more tendency to attract the electron compared to that of the hydrogen, fine. Therefore more of electron cloud will be towards the fluorine, so this will have the less electron cloud and the fluorine would have had the more electron cloud. Okay, so you should get this thinking. So here when you look at the periodic table, the s block elements, which is towards the right, which is towards the left of the periodic table, will have less electronegative character, okay, when compared to that of the element that is towards the right. Got it? So those halogens, oxygen family, nitrogen family will have more electronegative nature to that atom when compared to that of the s block elements, fine. So if you have to evaluate this one, if you're just gonna take hydrofluoric acid, it will obviously be in the solution form. When it is in the solution form, in the solution H will be positive state ion, which means in the form of H plus. Same way fluorine will be in the form of F minus ion. So that's how it's gonna be. So from that it has to be clear that fluorine has a greater tendency to attract the shared pair of electrons. Okay, so the way it's going to dissolve and all those things we will learn in the upcoming chapter, which is like equilibrium. Got it? As if now what you need to know regarding this electronegativity is when the atoms are bonded and it is in the bonded state, one of the atoms will dominate more in attracting the electron. Okay, so those atoms will have more electronegative nature into it. Therefore the value of electronegativity for those atoms is going to be higher, right? So the electronegativity will show a trend of increasing across the period. Fine. So as you move across the period, it will have more electronegative. Therefore, non-metals will comparatively be more electronegative when compared to that of the metals, because metals will readily lose the electron. Same way with the case of non-metals, it will easily absorb those electrons. Okay. So this is what you need to know regarding the electronegativity. As you move across the period, it's gonna increase. So what's gonna be the case with the case of moving down the group? As you move down the group, that's gonna decrease. Okay, it's the other way around, because as you move down the group, the attraction is gonna be less as the atomic radius is more. Okay, when it is more, the nucleus is not able to give more impact to that valence electrons, right? So this is the general trend that we see. Got it? It has to be clear. So as far as these four terms are concerned, which is atomic radius, ionization enthalpy, electron gate enthalpy, electronegativity, only the first one, it decreases across the period and it increases down the group. For the rest, all three concepts, which is like ionization, electron gain enthalpy, and then the electronegativity, it's going to follow the same trend, but you might have had some exceptions depending on the situation, but the trend is going to be the same, which is it increases across the period and then it decreases down the group. So that's going to be the trend for the last three concepts that we have learned. Okay, so here if you look across the period, electronegativity is going to increase across the period, electronegativity increases, and down the group electronegativity decreases. Okay, so this one has to be clear. Then how will I have to get the value? That's what we are going to see over here. So the electronegativity of any given element is not constant but is dependent on the following factors. Fine. So if you're just going to choose an element, it's not going to be constant. It just changes depending on these factors. So what are all the factors that's going to get involved? That's what we are going to see over here. So it depends on the state of hybridization. Electronegativity increases with S character in the hybridization. So do not want to worry about this term hybridization. We will learn all the different types of hybridization in the next chapter. Aside from, what you need to know is, with the increase in S character, you're going to have more electronegative nature to that particular element. I'll just take one simple example, that's going to be carbon. So in the case of carbon, it can form single bond, it can form double bond, and then the triple bond. Okay, so when it is in triple bond, the hybridization will be sp. When it is in double bond, the hybridization will be sp2, and when it is in single bond, okay, when it has single bond, it will be bonded to four different atoms. If that was the case, you would have got the hybridization to be sp3, right? When you have maximum number of bonds, which means triple bond, the hybridization is going to be sp, right? Do not want to worry about this hybridization. We will do it in the next chapter. Okay, so when you have got like sp hybridization, it's like a 50-50 share. 50% you would have got like s orbital involved and one p orbital would be involved. Therefore, that's going to be 50% share, and then the s nature would be like 50%. With the case of sp2 hybridization, so three orbitals would have been involved, one s orbital, and then the two p orbitals would be involved. Therefore, you would have got like 33, one third of the percentage of the orbitals. Therefore, that's going to be 33.3 percentage. Then with the case of sp3, that's obviously like 3p orbital and then one s orbital. So you would have got like 25% of s character, right? So with increase in s character, you would have got like more electronegativity, right? So here the electronegativity will be more for sp hybridization when compared to that of sp2 and then the sp3, right? So this is what you need to know. I just explained you with respect to carbon, so it will just work out with the case of nitrogen, oxygen, and all those other elements, right? Next, it also depends on another one parameter, that's going to be oxidation state of the element. Fine. So this one will come into picture when you have multiple valency to the element. So multiple valency will mainly be exhibited by the d block elements. Some of the p block elements will also exhibit multiple valency. So here, with increase of oxidation state of electronegativity increases. Okay. So if the oxidation state is going to be higher, then electronegativity is going to be higher, right? So here if you look over here, Fe3 plus, here the oxidation state is +3, here it's going to be +2. So Fe3 plus is actually ferric. Fe2 plus is ferrous. Okay, so if you compare these two stuff, ferric is going to have more electronegative nature when compared to that of Fe2 plus, even though these two are same element. The other example that is possible over here is copper. Okay, you will have like two valency to it, which one will be Cu2 plus and the other one will be Cu plus. If it is Cu plus, that will have less electronegative nature when compared to that of the Cu2 plus, right? More the oxidation state, more the electronegative nature to it, right? So these elements, when it has more oxidation state, it has more tendency to attract that shared electron pair to which this element is bonded, right? Got it? It has to be clear. So it depends on the two parameter. One is the state of hybridization and the other one will be the oxidation state of the element. Fine. So now I have just written one more statement. You should have already known this one. Fluorine has the highest electronegative, which is the most non-metallic. Okay, more the electronegative, it shows more non-metallic nature. So fluorine is towards the extreme right in the periodic table. Noble gases, we do not want to worry about that one because it has like perfectly stable configuration. So extreme right, you have got like fluorine, which is obviously most non-metallic and it has the highest electronegative nature to it. As you move down the group, that's going to decrease, right? So fluorine is at the top, therefore fluorine has the highest electronegative nature. Then towards the extreme left, you would have got like sodium. I mean, you would have got like sodium, potassium, right? So in that case, the last you would have got like rubidium, francium, cesium. So cesium will be the last element. Okay, so cesium will have the lowest electronegativity, right? So that would have got the lowest electronegativity and which is like most metallic of the periodic table, right? So fluorine, it is the highest it has the highest electronegative nature, and with the case of cesium, it has the lowest electronegative nature, right? So this is what you need to know regarding the ionization, I mean electronegativity. Now we will see the distinguish between the electron gain enthalpy and then the electronegativity. Okay, so what are the similarities and what are the difference? That's what we're going to see now. The first point that I've written over here is it is the tendency of an isolated atom to attract electron. Got it? So when you have an isolated atom and then it needs to pull one more electron towards it, what will be its tendency? How much amount of energy it is possible over there to release? So that is what is meant by electron gain enthalpy, obvious. Then with the case of electronegativity, it is a tendency of an atom in a combined state, which means it is already in a molecular state, that is in a molecule, to attract the shared pair of electrons. Okay, when it is in the molecular state and still it just pulls that electron cloud towards itself. Okay, so that tendency is called as electronegativity. It has to be obvious. Then it can be measured experimentally, which means the amount of energy released can be measured, okay, with respect to the heat change or the enthalpy change. But with the case of electronegativity, it's just a relative number. So based on the experiment that we do, we arrange those elements and then we give numbers to it, right? So you have certain pattern of giving that number. That's not needed over here, but it cannot be determined experimentally, which means it's not something you would have got related to energy of things of that sort, right? So this is a relative number. So based on the position, we are going to give that number. So the maximum number will be like 4. So that would be for the fluorine. So based on that, we will give rest all other numbers, right? So it's just a relative number that we are going to give. Okay, right? So electronegativity will be useful while determining the dipole moment and all those things within a molecule, right? Because there the bonded molecule, I mean the bonded atoms will involve in the dipole moment and all those stuff. Got it? So the final one is it is a constant quantity for a particular element. So for a particular element, that's going to be constant, but that's not the case over here. So depending on its hybridized state, depending on its oxidation state, that's going to vary. The electronegativity of an element is not constant. Fine. So this is the difference in between electron gain enthalpy and then the electronegativity, which is something that you need to know, right? Now you have to be clear with all the four concepts that we have seen related to periodic trends. The first one was atomic radius, and the next one was the ionization enthalpy. Then we did see like two different concepts, which were electron gain enthalpy and electronegativity. You have to be clear with all the concepts that we have seen. Finally, we will see the chemical trends, okay, that will be based on the acidic strength, right? So we will see that one in the next page. Next one is chemical reactivity and its periodic trends. So to know the trend of the chemical reactivity based on the periodic table, okay, across the period and around the group, first what you need to know is you should know the difference between the acid and then the base. Got it? How it's gonna behave when it is in the solution state, right? So to know that one, I've just taken you to the familiar examples, which will be HCl that's gonna react with the base, which is like acid. Same way NaOH, which will be the base, that's going to react with an acid. As far as H2O is concerned, this is neutral. If you put with the acid, it will behave like base. If you put with the base, it will behave like acid. So that's going to be the neutral state, fine. So we will learn more about this acid base in the chapter equilibrium. As if now, I'll just give you the overall understanding of the picture, right? So this understanding is needed, by the way, because with this understanding, I'll build the concept of acid and then the base pH value and all those things in the equilibrium chapter. Okay. So here you've got HCl and then the H2O. It's in the solution state. Got it? So we generally know acid will be an H plus donor. With the case of NaOH, that's going to be a base OH donor. Okay. So acid, it just readily gives the H plus ion. With the case of NaOH, it readily gives the OH minus ions, right? So that's how acid and base is going to behave. It's not necessary that in every single situation H plus should be the donor, right? Here in this situation, if you look closely, yeah, this is gonna give the H plus ion. So how is the H plus ion? That's gonna be electron deficient, right? So it will just pull the electron from the base. Okay. So something that has electron deficient nature into it will always be acid. Something that has extra excess of electrons or kind of that electron, it is able to give those electrons and pull the positive from the cation from the neighboring molecule. That's going to be base. Okay. So with the case of acid, that's going to be electron deficient, which means it will accept electron donor from the neighboring atom, from the neighboring molecule. With the case of base, that's going to be electron donor, which means it donates the electron and then pulls the positive charge from the neighboring molecule. Okay, so that's what it's going to happen over here. So here this HCl, that's going to give H plus ion to this base and it will pull the OH minus ion. So here HCl acid is gonna accept the electron, so it is an electron acceptor. With the case of base OH minus ion, that's gonna donate those electrons. Okay, so that's how it's gonna be. So if that's the case, here you will end up forming H plus. Okay, so that's gonna split and then you would have got like Cl minus, so it will be in aqueous state. Plus same way you would have got like Cl minus, that would be in the aqueous state. So this H plus ion, what will it do is it will just attach with this, it will just pull this OH minus ion from this H2O. Okay, so and then again it will form the H2O, right? So anyway, in this situation there wasn't any reaction between HCl and the other base. In the situation, the reaction was such that HCl was acid and then the base was like H2O. So you will end up getting the same thing again and again. If it reacted with some other NaOH base, it would have formed salt. That will be like NaCl, right? In this situation, this just split into two. This H plus ion, obviously it is able to give this H plus ion, which means it can accept the electron from this H2O, right? So here I can write this equation in this pattern also, which will be like, or in this pattern, which is going to be like H3O plus, which means here it gave this H plus ion and then it attracted this oxygen. Therefore, it just formed like H3O plus, because obviously this is H plus, that you're going to have one electron deficient. So together it will form like H3O plus. Got it? Same way the other one is going to be Cl minus. So these two stuff will also be in the aqueous state. So same way you could put this AQ. Now we should be clear with the understanding of the acid and base. So acid will be an electron acceptor. With the case of base, that's going to be the electron donor, right? So H3O plus, I can call this one as hydronium ion. Okay, I can call this one as, let me take a different color. So I can call this one as hydronium ion. Fine. So here, if you just look at this H3O plus, this H3O plus can give H plus ion, right? Therefore, this will behave like a conjugate acid in the situation because it can donate. Here, HCl gave this H plus ion and then it reacted with the base and it formed like H3O plus. So this H3O plus, what can it do is it can just give back that H plus ion. Therefore, this is acid over here. So this is the acid over there. With respect to this acid, you have formed H3O plus acid. So that's going to be conjugate acid, right? Okay, so that will come up equilibrium where this mixture and this mixture will be in certain ratios. Okay, so that ratio, that's called as equilibrium constant. We'll do all those stuff in the equilibrium chapter. So that will come a point, that will be the equilibrium between this HCl H2O and then H3O plus and then the Cl minus ions, right? Got it? So acid is a strong acid, it will undergo maximum dissolution with the case of HCl. So here you have got like H3O plus ion. I can call this one as conjugate acid. I can call this one as conjugate acid. Then what will this Cl minus be? So this Cl minus has been formed from the acid which has electron into it. So now it can actually donate this electron and then attract this H plus ion, right? Therefore, something that can donate electron is going to be conjugate base, right? Conjugate base. I'll tell you what is meant by Lewis acid, Lewis base afterwards. Okay. So this is going to be conjugate base. Okay. So this is what you need to know. So if there wasn't any involving of H plus ions and then the OH minus ions, and still if it can act as acid and base, that is when I'll call it as Lewis acid and then the Lewis base. So when you get into the intuition of Lewis acid and Lewis base, you shouldn't look for the H plus and then the OH minus ions. Okay. Something that can give electron and then pull the positive from the neighboring molecule, that's going to be Lewis base. Okay. For example, in H3, that will have that electron, okay, some lone pair of electrons into it. So what it can do is it can just pull the neighboring H plus ion and it can form like NH4 plus. So I can consider that NH3 to be Lewis base, something that can give electron pair and then pull that positive charge. That's going to be Lewis base. Other way around is for the Lewis acid, right? So when you don't have H plus and OH minus ions involved, I'll call that one as Lewis acid and Lewis base based on the electron accepting and donating nature, right? Yeah, it has to be clear. So in the case of NaOH, we know that's going to be base. So then what should be my water? It has to behave like an acid, right? As water is a neutral, it can behave both as acid and base depending on the molecule that I'm going to choose, okay? Depending on the composition that I'm going to choose. Here I have chosen NaOH, which is going to be the base. Got it? So NaOH plus H2O, how does it going to react? This will produce Na plus OH minus ions, right? So here if you look, this Na plus, what it can do, it can accept the electron, isn't it? Yes, therefore this will behave as conjugate acid. With the case of OH minus, this can behave as conjugate acid. Yeah, this can accept the electron. With the case of OH minus ion, it's an electron donor, therefore that has to be conjugate acid base, right? Conjugate base. This notion has to be clear, right? You shouldn't have any doubt in what I've told over here. So I have just given you like overall picture of what is meant by acid and then the base. I'll just tell you how to find the equilibrium constant and other stuff, pH value and all those things in the upcoming chapter, which will be like equilibrium. As if now, this is what you need to know regarding the acid and base. So acid will generally donate H plus ion or it will be a good electron acceptor, okay? With the case of base, it can donate OH minus ion or it will be a good electron donor. That's what you need to know with respect to acid and base. That foundation is enough to learn the chemical trends. Okay, that is needed. First, we will learn with respect to oxides. Okay, so oxides actually means you can get an element and then put oxygen into it depending on the valency. Fine. So it depends. So an atom can have multiple oxygen into it depending on the valency. As if now, if you just put only oxygen into it, that is called as oxides. Oxides are chemical compound with one or more oxygen atoms combined with another element. Alright, if you look over here, this sulfur, this is a p block element. It has oxygen attached to it. So this is actually oxide. Fine. So with respect to oxide, two things also possible. One is like basic oxide and the other one is the acidic oxide, right? First, let me tell you how does this acidic oxide behave. Then we'll just see the basic oxides. Then we will see the periodic trend. How does it change from basic to acidic? And there is something called amphoteric, which means it behaves as both acid and then the base. If you put like acid into it, it will behave like a base. If you put base into it, it will behave like an acid. So that will have both those properties into it. Okay, so this is what you need to know regarding the oxide. To get an oxide, what you need to do is you just have to put an element and you have to make it combine with oxygen. That's it, finished. There shouldn't be any other element involved. If that's going to be the case, that's what is meant by oxides. Fine. So first I'll take the acidic oxides. So for the example of acidic oxides, the non-metals that I've chosen over here is the sulfur and then the carbon, right? Acidic oxides are the oxides of non-metals. So the first thing that you need to know is if you're going to take a non-metal and then put oxygen into it, most probably that's going to be acidic oxides. Not that it can be amphoteric depending on the situation, but that wouldn't be like basic oxide. That's not possible, right? So the non-metals, when it generally combines with the oxygen, it forms acidic oxides. So what will be the non-metals? Those p block elements. That's going to get you the acidic oxides, right? And these acid anhydrides, fine. So I'll just call these acidic oxide as acid anhydrides. I'll tell you in a minute what is meant by acid anhydride. Forms oxyacids with water. So when this acidic oxide reacts with water, it forms oxyacids. Okay. So obviously, when an acid, if you have an acid and then remove water from it, that will form acidic oxides, right? So acidic oxide and acid anhydrides both are just the same thing. Take an oxy acid, take a normal acid and then remove H2O from it, it will obviously form acid anhydride, because anhydride is something that you have removed water from it. So whenever you remove water from a chemical compound, you'll call it as anhydride. So that's the chemistry term that we generally use. You'll get used to this stuff. Okay, this will keep on repeating in the organic chemistry. So here acid anhydrides is also known as acidic oxide, right? You should know that thing. So now here the example that I've taken for the acidic oxides are SO2, SO3 and then the CO2, right? So these three acidic oxide is going to react with the water. Then what will it form? It will form the oxyacids, right? So here, how the reaction procedures, I just know this is going to be the this is going to be acid, right? It's going to react with the H2O. So obviously what it will do is it will just, this is electron deficient or electron acceptor. So what it will do is it will just accept this lone pair of electrons from this OH minus ions. Okay, so it will just accept it, and then there will be a bond formed between sulfur and then the OH. Then there will be a breakage of bond with the case of oxygen. So that oxygen will accommodate this H plus ions. Okay. So here this attracts that OH minus ion. So this is gonna lose this OH minus ion and SO2 is gonna attract that one. Right. Therefore SO2 plus H2O, that gives you the sulfurous acid. So that's gonna be H2SO3 in the situation. So I'll call it as sulfurous acid. Right. So the next one will be sulfuric acid. So this is called as sulfurous acid. Okay. So the next one, you have got like SO3, that's gonna pull the same way. It's gonna pull that OH minus ion from this H2O, and that's gonna get bonded. Then you will end up forming H2SO4, which will be sulfuric acid, right? So here you would have got H2SO4. So this will give you sulfuric acid. Next equation is carbon dioxide CO2. It reacts with H2O, and what will it form? It will form like H2CO3. Same way, this carbon will be an electron acceptor. OH minus will be the electron donor, and then it gives you H2CO3. Okay, it will give you H2CO3. So this is gonna be carbonic acid. This will be carbonic acid. You have to be clear with the acidic oxides that I've written over here. Right. Next, let us see some other examples of the oxyacids, right? And then we'll see the basic oxides. So here with the case of oxyacid, what should it form if it combines with the base? Obviously, if it combines with the base, it has to form the salt, right? So SO2, I know it is an acid. If it combines with the base, it has to react with the base, because this one is acid, this one is base. If these two stuff reacts, it will form the salt, and then water will be the another one product over there. Therefore, here if I have to balance those valencies, obviously I would have got Na2SO3, right? And then you would have formed H2O. So that's how it's going to get balanced. So you would have got Na2SO3. So that's going to be the salt over here. So which is like sodium sulfite. Okay. If it was like SO4, that's going to be sulfate. This is going to be sulfite. Fine. We will learn this stuff in the P block elements. As if now it formed the salt, right? So here it just reacted with this Na. Here it just reacted with this Na, and then SO2 reacted with this Na, and then it formed the salt. Fine. Then what will be the byproduct over here? That's gonna be H2O. This will be my salt. Fine. Okay, it has to be clear. Then obviously this reaction will work out because SO2 is acidic in nature. If it was a base, then this reaction will not work out, which clearly suggests this is not a base, right? If you put acid with the base, the reaction should proceed. Fine. Then let us see some example for the basic oxides. Obviously group 1 and then the group 2 elements are basic oxides. The first group and then the second group. Yeah, they are called as alkali metals and alkaline earth metals. We will do it. So these oxides are basic in nature, right? I have already told you towards the left, that's going to be basic. As you move across the period, acidic nature increases, right? So when Na2O reacts with H2O, what it does is this is basic in nature. So basic will give you the electron and then it accepts the H plus ions, isn't it? So here this will behave like an acid and this will behave like an base, which means this is gonna pull H plus ions and then it will form NaOH and it will release one of the Na plus ions, right? So that Na plus and then the OH will form NaOH. So here in this situation, two NaOH would have been formed. So it will give you two NaOH, right? So this is base, therefore this will give the electron and it will accept the proton, okay? If the same will work out over here, so here what it does is it will just pull the H plus ions and then CaOH, as it is divalent, it will form like, it will also pull one more OH minus ion, therefore together it will give you CaOH2, right? It has to be clear. So here what would have been formed is CaOH twice, right? This one has to be clear. So here basic anhydrates reacts with the acid to form salt. Obviously, this reaction should proceed. If you put like MgO against NaOH, that's not going to react. Got it? Here this is going to be base, therefore it reacts with the acid. So when these two stuff reacts, it will form. Yeah, it will form like MgCl2. That will be my Mg is going to be divalent, therefore it will form like MgCl2 and then the H2O plus H2O. That will be the byproduct. So the salt is formed in the situation. Got it? The reaction will proceed and the salt will be formed. It has to be clear, no doubt should be there. Then you have got like amphoteric oxides, and then the final one will be the neutral oxides, right? I've already told you, amphoteric oxide behave as both acid and then the base. See, as far as acidic oxides and basic oxides are concerned, only if you put acidic oxide against the base, you'll end up getting the salt. Got it? Only if you put basic oxides against the acid, that's going to be base, right? So basic oxides against the acid will give you the salt. For the amphoteric oxide, you can put in both those ways. If you put like acid, it will behave like a base. If you put like base, it will behave like an acid. So that is what is meant by amphoteric oxides. So amphoteric oxides exhibit both basic as well as acidic properties. See, do not want to worry about the equations that I have generated over here, that I have written over here. The point is, you should know these stuff are amphoteric in nature. Do not want to worry about the product that has been formed in the situation, right? So zinc oxide, it will react with the HCl, it will work out and it will form zinc chloride. Salt will be precipitated. Same way, zinc oxide, when it reacts with the base, NaOH, sodium zincate, a salt is formed and then the water will be the byproduct. So these two reactions will proceed because it is amphoteric in nature. So zinc oxide is an amphoteric oxide. Then you have got like Al2O3. This is in the p block element. Still, this will behave as both acid and then the base. So when it reacts with acid, it will form Al2SO4 thrice. That's going to be basic. Same way, when it reacts with NaOH, it will form NaAlO2. Do not want to worry about the naming and all those stuff. What you need to know is zinc oxide and then the aluminum oxide, Al2O3. These two stuff are amphoteric oxide, which means it can react both with acid and then the base, right? Yeah, I'll tell you what are all the oxides that behaves as an amphoteric oxides in the next page. As if now, you just need to know there are elements which can behave as both acid and base. I'll call it as amphoteric oxide. Finally, you have got like neutral oxides. this will not react with both base and then the acid, right? So I've given you like 4 examples. Just memorize these 4 examples. That's it, finished. So neutral oxide shows neither basic nor acidic properties and hence do not form salts when reacted with acid or base. You do whatever you just how much ever you want, there wouldn't be any reaction that's gonna get proceeded, right? If that's the case, they are called as neutral oxide. Examples are, most of them are gases: carbon monoxide, N2, that's going to be nitrous oxide, NO, nitric oxide. Final one is like MnO2, right? So you have got like carbon monoxide, nitrous oxide, nitric oxide, and then manganese dioxide, right? So just remember these 4 examples. That's it, right? In the option, they'll give you like either one of those 4 elements. That's either one of these 4 molecules, right? So this is sufficient. Carbon monoxide, N2O, NO, MnO2, nitrous, nitric, manganese dioxide, right? You have to be clear with this examples that I've told you. Then you will see the trends and all those stuff in the next page, right? Now we can see the trend across the period and around the group. We have already discussed, we know towards the left that's going to be strongly basic, and towards the right that's going to be strongly acidic, right? We have already discussed, isn't it? Therefore acidic nature increases across the period, right? Acidic nature increases across the period. If they are asking you to get the basic nature, it has to be other way around, which means basic nature decreases across the period, right? Here I'm just going to discuss only one step, that's acidic nature. If in the question they're asking you to get the basic nature, just flip it, it's going to be other way around, that's it. Got it? So if you look over here, Na2O is strongly basic, MgO is basic, Al2O3 we have seen earlier, that's going to be amphoteric. Then SiO2, P2O5, SO3, C, L2O3, all those stuff, Cl2O7, all those stuff are going to be acidic in nature, right? So do not want to worry about this combination of oxygen into it. Just know it's going to be, if an element just combines with the oxygen depending on the valency, then the count of oxygen is going to differ. Whatever the case it is, if it's going to combine with the oxygen, it's going to be acidic or basic depending on its position in the periodic table, right? So all those oxygen count and all those things we will learn in the p block elements. As if now this is what you need to know regarding across the period, right? Then what should be the case with respect to down the group? It has to be other way around, right? So down the group, acidic nature, yeah, it has to decrease, right? It decreases. So here Li2O will be more acidic when compared to that of Na2O, K2O and Rb2O, but we know this is for the basic stuff, right? So Na2O in itself is basic. If you just compare this Na2O with the Li2O, it simply means this is going to be more acidic when compared to that of this one, right? So as you move down the group, what's going to happen is it's the other way around for moving across the period. So here as you move down the group, that's going to be other way around. Therefore acidic nature has to decrease, right? So acidic nature decreases, which means Li2O will be more acidic. Yeah, Li2O will be more acidic, and then Na2O when compared to that of Na2O, and then it goes up, right? So if you have to get the basic nature, then basic nature increases. So Rb2O will be more basic, then comes the K2O, then comes Na2O, then comes the Li2O, right? So here I'm just written based on the acidic nature, right? You have to be clear with the trend that I've told above. Then we will see which one will be basic and then the which one will be acidic, right? You just have to remember this one as such, because in the question they'll just ask you, so they'll give you something, zinc oxide, aluminum oxide, whatever it is. Okay, so they'll give you those for those molecules and they'll ask you to match which one is base, which one is acidic, right? If you get that combination, you just have to remember this pattern. Once you remember this pattern, you can easily match, right? You'll get like 3-4 sums. While doing it, this graph will be handy, right? How you should actually memorize this one is, just look from top to down: lithium, sodium, potassium, rubidium, cesium, right? So this first group elements, this will be basic, right? So the purple represents basic oxide. With the case of second, it starts with beryllium, right? So beryllium, then magnesium, calcium, strontium, barium. So this beryllium is the only element that's going to be amphoteric, rest all other will be basic as usual. Then just go directly to this boron, carbon, nitrogen, oxygen family. So this is going to be the p block elements. Okay, so boron, bag it, boron, aluminum, gallium, indium, thallium, right? So this is the first p block element, isn't it? That boron family. In that boron family, this one boron is going to be acidic in nature, aluminum and then the gallium, so that's going to be amphoteric. Indium and thallium will be basic, right? You just have to remember this pattern as such. You're left with no other choice. Okay, so here it's going to be boron, aluminum, gallium, indium, thallium. Thallium is going to be basic. So this is the only two element that's going to have basic oxides, right? So with the case of 14, carbon, silicon, germanium, tin, lead, right? So here carbon, silicon, these first two are going to be acidic oxides. These three are going to be amphoteric oxides, right? So then you have got like, yeah, sulfur family, that's going to be nitrogen family. So that's going to be nitrogen, phosphorus, arsenic, and arsenic, antimony, bismuth, right? So arsenic, antimony, bismuth are amphoteric. These two are acidic. Rest these two series, which will be the oxygen family and then the halogen family. These two stuff are going to have acidic oxides only. So oxygen, sulfur, selenium, tellurium, polonium. It's going to be acidic oxides. Then you would have got like fluorine, chlorine, bromine, iodine, and then atrium, right? So these stuff are going to be acidic oxide. So to remember this pattern easily, the way I remember is just get this amphoteric oxide. So once you know this amphoteric oxides, something that is towards the left is going to be basic, something that's towards the right is going to be acidic, right? So you just need to get this, you just need to memorize this elements alone. So for the second, the first one, for the group 2, the first one alone will be amphoteric. Then rest all other stuff over here is going to be basic, right? So that's how you need to remember this one. So beryllium. Then for the boron family, just leave the second two will be amphoteric, which is going to be aluminum and then the gallium. So the one that is down is going to be basic. The one that is up is going to be acidic. Then with respect to this carbon and nitrogen family, last three will be amphoteric. Okay, so the last three over there is going to be germanium, tin, lead. And with the case of nitrogen family, that's going to be arsenic, antimony, bismuth, right? So just remember this amphoteric oxides alone. Something that's towards the left is going to be basic, something that's towards the right is going to be acidic, right? Right. So do not want to know this entire series. Just remember that amphoteric oxide. So the amphoteric oxide that you need to remember will be the beryllium, and then you would have got like aluminum and then the gallium, right? Then last three elements with respect to carbon and then the nitrogen family. So this is something that you need to remember. Once you are familiar with these elements, something that is towards the left is going to be basic, and the elements towards the right are going to be acidic, right? Yeah, that's done. And there is this only one extra D block element that I'm going to give you, zinc oxide. That's acidic, that's amphoteric in nature, right? Only once they have asked such a question, that's why I've given you over here. So oxides of zinc are amphoteric in nature, right? Next, we can see the trend for oxyacids. So what is oxyacids? You just take acidic anhydride and mix it with the water. You'll end up getting the oxyacids, right? We have discussed earlier. Here I'm just going to see the trend across the period and down the group, right? You just have to memorize this one as such. Fine. So across the period, same way, it's going to increase. H3BO3, H2CO3, HNO3. I have already told you these are these oxides, as you move across the period, it's going to have more acidic nature. So same thing will work out for the oxyacids. Across the period, the acidic nature is going to increase. Fine. So across the period, acidic nature increases. Just remember it. Then what will happen down the group? That's going to decrease, right? So same thing. So here if I just put the arrow mark, that's going to be this way, in this fashion. Okay. Next, you have got for the down the group. With the case of down the group, acidic nature decreases. That's going to be other way around. So the arrow will be pointing this way. It has to be clear. So acidic nature decreases. Got it? This will be in the descending order. Next one will be the oxyacids of chlorine. So chlorine, this halogen stuff can have different valency and can form multiple oxyacids. For example, HClO, HClO2, HClO3, and then HClO4. Okay. So before we have seen the oxides of chlorine, that's gonna be Cl2O7, isn't it? So this is strongly acidic, right? I've told you this in this also the acidic nature increases. Oh, I just didn't put the arrows. So that's gonna be this way. It's this, right? Yeah, fine. So same way, if you look over here, I've told you here also acidic nature is gonna increase when you have like more count of oxygen to it. The acidic nature increases. Cl2O7 has a greater acidic nature, then by the same argument here, as you plug in more oxygen into it, acidic nature has to increase, right? Therefore, with respect to this chlorine, which shows multiple valencies and it forms multiple molecules with oxygen and then the hydrogen, that's the case, then acidic nature increases with increase in the count of the oxygen, right? Therefore, here acidic nature increases. Got it? Therefore, I just need to put in this direction. That's gonna be acidic nature increases, right? Therefore, the order should be ascending order. Yeah, HClO, which has less acidic nature compared to HClO2, and then it goes on, right? You have to be clear with this one, the oxy acid that I've told over here. Final one that is left is hydrates, right? So you have to remember this stuff as such. Okay, so across the period, so if you look at this one, NH3, H2O, HF, we obviously know HF is acid, right? HCl is acid, therefore, acidic nature increases across the period. Acidic nature increases. So you would have got arrow mark in this fashion, arrow which is going to be this way, increases, ascending order. Okay, then down the group, acidic nature in the situation, even and down the group, acidic nature is gonna increase. Right? Yeah, you have to remember this one, right? So across the period, also it increases. Same way down the group, also it increases. So if you compare HF, HCl, HBr, HI will be more acidic. So we'll get the arrow in this fashion. It's gonna be HF less than HCl, HI. The reason is because this I minus HF, right? H and then the iodine. So iodine has bigger atomic radius when compared to that of the hydrogen. Therefore, the bond length will be greater. So if the bond length was greater, it will be easy for me to break. In the case of HF, this is like closely bonded, therefore it is hard for me to break. Even though fluorine is highly electronegative, breaking this bond is actually tough. With the case of HI, the bond length is greater, therefore it is easy for me to break this bond, which will so that I can easily produce this H plus ion, which will act as an electron acceptor, right? So this is what you need to know. So whatever it is, across the period, acidic nature increases. Same way down the group, acidic nature increases. It's a kind of exception. So that's something that you need to know regarding the hydrates. Then we are just only with one chemistry term which you need to know, which is called as amphiprotic. Okay. So amphiprotic is same as that of the amphoteric. All amphiprotic species are amphoteric. So only difference over here is here that hydrogen will be involved. Okay. So amphiprotic species acts as both acid and base by accepting or donating H plus ion. So with the case of Al2O3, which we saw as an amphoteric, there like Al2O3, there wasn't any hydrogen involved. If H plus ion was involved in the reaction, then I'll call that one as amphiprotic. Okay, so that specific term protic, it represents that there is an involvement of H plus ion. Either it got donated or it got accepted, right? If it donates, then it's gonna behave like an acid. If it accepts, then it's gonna behave like a base. Okay, so here the example that I'm going to take over here is HSO4 minus. First, in the first situation, it's going to, what it does is it's going to accept H plus ion. Okay, so if it accepts H plus ions, then it will behave like a base, right? So it will form H2SO4 and then plus OH minus ions, right? So this will behave like a base. Same way, in the second situation, it's gonna donate this H plus ion. If it donates, then obviously it's gonna behave like an acid. So you'd have got something like this. SO4 2 minus because it has donated H plus ion. That electron will be left with the SO4 and then you would have got H3O plus, right? Yeah. Here also it just behave both as acid. Yeah, both as acid and then the base. you can call this one as amphoteric, but I'll just use extra specific term to it because H plus ion got involved, so that I'll call it as amphiprotic. So if you get a term amphiprotic, it is same as that of the amphoteric, but the point is H plus got involved, right? Same way, if you just take water in itself, that's a neutral thing. So it will have some combination of H plus and OH minus ions into it. That will be in the 10 power minus 7. We'll do it in equilibrium. But anyway, it will have some combination of H plus and then the OH minus ions, right? So in this situation, one will behave as an acid and the other one will behave as a base. So one will give you H plus and the other one is going to receive. So the ion that got involved over here is H plus ions. Therefore, even with the neutral solution, water, I can call it as amphiprotic, which means one can give H plus ion, same way one can accept the H plus ions, right? Got it? This is what you need to know regarding the amphiprotic, right? So you should be clear with all the concepts that we have discussed. We saw electron gain enthalpy. Yeah, right. How much energy is released if I have to push in an electron into it? Either it can be released or it can be absorbed, depending on the situation, right? You should be clear with all those exceptions that I've taught you. Then we did see like electronegativity. What is electronegativity? When a molecule is bonded, the capacity of particular atom to attract that shared electron pair towards itself, right? It wouldn't attract so much that the bond's gonna break, but it has a maximum tendency towards attract towards itself. Fluorine has the highest electronegativity, cesium had the lowest least electronegativity. So it's not a constant term with respect to the element because it can vary depending on the hybridization and then the oxidation state. You're gonna be clear with that stuff. Then finally, we saw the trend based on the chemical reactivity, right? So to know that one, I just told you what is meant by acid and base. You gotta be clear with that logic. Okay, so acid is something that is electron deficient, base is something that's electron rich or something that can donate. Electron donor is base, electron acceptor is going to be the acid, right? You have to be clear with that one. Then we saw the trends for oxides and then oxyacids and then the hydrides, right? You have to be clear with all those stuff that we have discussed. And finally, we did see that one important term which is called as amphiprotic, right? You should be clear with all the concepts that we have discussed. You shouldn't have any doubt. With this entire lesson gets completed. Same way this video also gets completed. Bye.